Good morning to the people online as well. So today we are going to switch gears. Yesterday at the end we talked about the largest accelerator, the wafer scale accelerator with trillions of transistors. So today we are going to go from ginormous to tiny. So we are going to talk about the area of TinyML. And as you may guess, that kind of tries to go to the other extreme of the AI world. So instead of being in the cloud on big servers that consume megawatts of power, now we are on portable devices, battery powered, some of them even maybe with energy harvesting that need to consume very little power. Of course, they are not going to have the performance of the really big ones, but we need to still be able to do kind of AI operations at the edge, as it's called. So we talked about this dichotomy between cloud and edge. Again, I mentioned this several times already in the past few days. Engineering is all about trade-offs. So, you give an engineer a function. If you just give the function, the engineer cannot really build a system without knowing, how much it should cost, how much power, how much the size, the weight. So again, the function is still going to be AI. That we are still going to have models with layers, with neural networks, with weights. We are still going to try to do, similar operations, but, with much more constraints. So here are, some examples of, devices where AI is necessary, desired, and, already kind of available. Probably the most spectacular lately have been these what's called AR, VR, augmented reality and virtual reality, so goggles. And I'm not sure anyone has tried the Apple goggles in the probably. So, it's been a flop commercially because it's very expensive. So, those goggles cost like $3,000. It's really ridiculously expensive. But I swear the experience is amazing. So I went to an Apple store, so you can, you need to actually sign up, and you get like a half hour with an Apple employee, kind of demoing it. But it's really amazing. So I would suggest if you go to a place that has an Apple store, go and make a demo because, it's really an amazing experience. And it's kind of, it's kind of, you can see the future. Eventually it's not going to cost $3,000. And right now it's also very bulky. So, it's kind of heavy and uncomfortable, but the experience is really amazing. But, there are everything else, including toasters that have AI nowadays. And again, we are talking, instead of megawatts, we are talking milliwatts. Okay, so it's working. Well, it's fine. Oh, there is a button here. Oh, yes. Okay. Yeah, so again, if we talk machine learning nowadays, we talk about deep neural networks, and I'm not going to go into this, but you can do kind of back of the envelope calculations that if if you have, 10 to the 9 operations and it needs to be in some milliwatts, then you need, 1,000 TOPS per watt. And we already talked about, this IRIS project from Vivian Z. So this is actually a slide from her presentation. So in some sense, you already were introduced to something related to, to TinyML, so to speak. Here is another view. This is from IMEC. About where TinyML fits in the landscape of kind of AI convolutional neural networks processors, and you have the power on the x-axis and the peak performance on the y-axis, and again TinyML is needs to be on the as high in terms of performance, but as low power. So it's, it's a relatively tough to be in. And, some of these ones here are, too much power basically for TinyML. So again, in terms of metrics, the aspect that we really care about is kind of what's the energy per inference, because that's really going to be the ultimate energy efficiency. And if you break it down into how many operations per inference you need, and then what's the energy per operation, you get that energy per inference. So basically, what you really want to do is to minimize the number of operations per inference, and of course, minimize the energy per operation. And both of those are tough, but they are kind of coming from two different fields, so to speak. To minimize the operations per inference, that comes from the architecture and from the model and all those things. And the energy per operation comes from the circuit. So you basically have kind of two ways to try to get to the point of energy per inference. And again, there are some things that if you just look at, because many accelerators actually, the metric that they mention is this TOPS per watt. The problem if you just do TOPS per watt is that that can still be very inefficient. It can have a very high TOPS per watt, but if you need a lot of operations to do your inference, it's still going to not be, energy enough. And then, some of the reasons for that is basically you can have many operations that are being basically redundant. And the other is, what is an operation? Because, many times, an operation can be quoted for very low precision or very high precision. And, is it multiplies, is it adds, is it max? And the issue is that, we do want to have these low precision operations, but sometimes what that means is that the model needs to have, more layers or more, do more operations, that at the end of the day, you still don't gain in the energy efficiency. Again, just to give you an idea of how tough some of these requirements are. If you look just at a basic NAND gate, the energy per operation, in a relatively mature but still advanced 28 nanometer, this is a fully depleted SOI. Basically, it's about 0.2 femtojoules, which is equivalent to 5,000 TOPS per watt, which is really not that high. If you were to just build a straightforward, hardware implementation, pure hardware implementation of a network that is not the most complex one. Let's say if you have 1 billion connections and you make some assumptions about the multipliers, the adders, how many full adders are needed in a multiplier, how many full adders are needed in an adder, if they are 8-bit. And then, if you do some simple calculations, you see that the area of your chip would be, 100,000 millimeters square. So that would cost, basically it's larger than the wafer that. So the point is you cannot implement, kind of one of these neural networks directly as they are. So you really need to implement accelerators the way we've been talking about, like something like this. So in some sense, we complain about the von Neumann architecture, but because of in many ways, I think I showed you that that's cross section with the wires and the transistors. I think in many ways it's because of that. Unlike maybe what we would think, we cannot really implement a neural network the way maybe how our brain is implemented. So our brain really does use something like this. There is no explicit memory processing element and whatever, but it has to do with the the characteristics of the biological neuron system, with the neurons and the synapses and the axons and all that. And the metrics of those compared to the metrics that we are able to make with our CMOS technology. And with our CMOS technology, it's basically infeasible to implement, to really map one of these networks to hardware, in a kind of in this brute force way in which you really implement everything in hardware. So you do need this kind of von Neumann split between memory and processing elements so that you can get something that's manufacturable with our technology. And again, this is really how an accelerator kind of has to look like. I think that's the argument of this. And again, just a little bit of the scale. If you compare an SRAM cell with with a car, and then if you compare the and again, this is from Vivian Z's presentation. If you compare the size of a chip, then going across one of these chips is the same as going, this is in Silicon Valley, basically Stanford and some a place nearby. And then basically this is about going across the chip from the SRAM and then going just in the register file. Again, this is the Stanford, campus, and you just go across the, the highway to, to the Stanford downtown.
So basically, this was the analogy for memory.
Yeah. Yes. Yeah. So it's basically the analogy of, the SRAM cell versus going with a car across town. And so basically going in from the SRAM cell, from the SRAM cell to the memory array, to the PE array, and going from the basically RF register file in the PE across, Any other questions I should actually ask? And again, to kind of put numbers here, the DRAM has about 100 megabytes, and there's about 10 picojoules per bit. The cache SRAM on the accelerator, it's about 100 kilobytes, so 1,000 times less, but it's 10 times more energy efficient. It's 1 picojoule per bit. The second, in this case, there are two levels, it's like level 1 and level 2 cache. So 1 kilobyte and 0.1 picojoule per bit. And then the register file is about 100 bytes, and it's, again, 10 femtojoules per bit. And so that's just the kind of the memory part, and the computation part. An add is about 30 femtojoules, and the multiply about 200 femtojoules. So you see that, again, in the Iris presentation, there was a 1-and-1 between the operations and the register file. And again, this is per bit. So if you now want per 16 bits, or then it will be kind of 1-to-1 between, you'd get about 160 here and about 200 here for the multiply. So it's a good approximation. And the the 1 millimeter wire, again, it's about 200 femtojoules.
So this is that 1 millimeter is basically the amount of energy required to charge the capacitance of that particular wire at a particular clock frequency.
This is energy, so there is no frequency. So just, So just one kind of transfer. So one switching event. Yeah. Any other? Again, so, I'm not going to get into, so it's some more arguments against external DRAM. And I'm not going to get into the numbers, but the point is, for TinyML, sometimes they are so tiny that hopefully you don't need this external DRAM. This is something that, again, we saw we saw an example of this in the Iris presentation, but this is another example, and it's a different accelerator, but it's kind of a similar argument about the different layers. It happens to be the same model as in the Iris, so it has 5 layers, convolutional layers, and 2 fully connected layers. And again, it's kind of the same, partitioning into, the arithmetic, the ALU, the external DRAM, the cache, the buffer, the register file, and then I'm not sure what the array really means here. yeah, I'm not sure what the array means because it doesn't even come into the picture here. But again, the different layers would have different power consumption, and like in the Iris, actually, if you remember from yesterday, the fully connected layers had more power in the DRAM because again, they were not using that much the register file, and the internal layers have more on the register file because they take advantage of this reuse in the layers while they do the computation. Again, there is some math here, and I'm not going to go into that. Again, you are going to get these slides, and you can go over them. But again, a processing element, and this one looks a lot like, like any other. So there is it looks a little bit like a CPU too, because it has a program counter and kind of an instruction memory and a data memory, and there is a register file, and basically the program counter determines which registers are the source, the two sources for the operation. And then, a register for the destination. Then, the two A and B operands go into the ALU, the operation happens, and the result goes into the destination register. And again, if you go on each of these energies, so you have the energy for the register file, you have the energy for the actual operation, and again, a multiply and an add, and then some energy for communication based on those wires that you go there, and again, some femtofarads. I'm not sure why they are farads there. Femtojoules is probably femtojoules. Yeah, it's yeah, this is a typo. So 3 times 80 femtojoules. That's for the register. 2 reads and 1 write. I guess 230. They were on the previous slide. So 30 is the add, 200 is the multiply, and the 80 is for the for the wires, the whatever, the 1 millimeter, I guess, the wire. So again, you get about 3.6 TOPS per watt, which is not a lot, but it is what it is. Yeah. Why is it a divide by 2? That's a good question. Yeah, not sure why there is a divide by 2, to be honest.
I was first thinking it was because we are doing 2 operations like multiply and add, but the energy consumed for multiplication is different than the addition, right? So it doesn't make sense to divide by 2. No. There are 2 operations that we are performing. Like one is the multiplication. No, it's not about the different number of operations. Number of operations is to multiply and add.
Yeah, so the assumption is that you do a fused multiply and add inside the ALU. So yeah, I'm a little bit stumped, to be honest, where that 2 is coming from. Yeah. I'll look during the break. I'll try to think about this. Yeah. Oops. So yeah, this is kind of another table that summarizes some results like, and let's move on. So this is more from a circuits perspective. If you start looking at the operations, in terms of, multipliers and circuits, again, so I think this slide is a little bit off the topic. Okay, so let's get to TinyML. I mean, this was more of an introduction, and probably I should have taken some of these slides out because this is where I was going to get to. So the TinyML, and TinyML is still quite in flux. Well, like the whole AI world, but in some sense, I think people at the edge are trying to figure out, because TinyML has not yet made the impact that, these large AI models have made. So, in some sense, it's still a very much emerging area. And there are not that many companies that play in this TinyML kind of field. At the same time, you can say that, most companies are going there because there is this, overlap between TinyML and, any embedded system. So on one hand, kind of pure TinyML companies are very few, but at the same time, all the embedded systems companies are moving into this area. So, but they are still kind of trying to figure out, I think, it's not clear when, it's more of a TinyML system than, just an embedded system that now has some AI capabilities. But, this is kind of, an example of an Arduino Nano, which is, a typical embedded system, but now you kind of use it for TinyML. And again, if you go to TinyML from the machine learning AI area, TinyML, you can define it as, a way to get a large model that runs, kind of on a conventional system and do something to it, make it smaller, with different methods in a way that can run efficiently on a low power system. And if you come at it from the embedded system world, you basically have something that's battery operated, doesn't have a lot of capabilities, but now you want to run some AI, applications. And we'll talk a little bit more about this, but you are basically going to use, we use PyTorch, and I mentioned when we talked about PyTorch that there are, several other alternatives. One of them is TensorFlow. Well, for TinyML, there is, TensorFlow Lite, which again is trying to have, a similar kind of front end. But again, in terms of the back end, you really want to target these TinyML applications. Again, some more about TinyML. Something that's important actually, and this, for those of you that are planning to do research in this area, I think this is a very important distinction. So until now, we talked about the fact that TinyML has to be, much more energy efficient, run more efficiently, battery, whatever. But the big difference is where the data is coming from for these TinyML systems. Because typically for cloud systems, the data comes from some memory somewhere. So, in many ways, the data is a document, are some images on the internet, some videos, whatever. For TinyML, most of the time, the data comes directly from sensors. So the data comes from, a camera that provides a stream, comes from a microphone that captures sound from, your iPhone. So interacting directly with the sensor puts some, interesting constraints on the model. And maybe, some of the things that we're discussing in terms of throughput versus latency start to switch for TinyML. Because in the cloud, many times you can take advantage of this batching where, for example, if it's, OpenAI cloud for ChatGPT, many users are, accessing at the same time, and the system can take advantage of that and parallelize many of the things in a way that, still satisfies all the users, but, gets more efficient because it can process many of them in parallel. And that's rarely the case for TinyML, because again, TinyML typically has, just one camera, one microphone, one. So there is no, opportunity to take advantage of some parallelism that is available in the cloud. And the other is that, it's also very much real time. In the cloud, you can, stream the data to these AI models, kind of independent, at the rate that they can absorb them. If they can absorb them really fast, you can, send them fast. If they absorb the data slower, so there is no real-time element. But here, because, the camera, looks at whatever happens, this is a very real time. So, you cannot speed it up, you cannot fast forward, and you cannot really slow down because you are going to lose frames. So there are some interesting constraints related to that. Yeah.
ChatGPT, we want the responses to be in the real time as well.
Well, that's not real time. That's real. You see, it's different. Real time doesn't mean fast. There is, so, this is a misconception about, and that, there is a whole, and this is unrelated to AI, but if you go and, you Google, you look at, real time systems, you will see that real time doesn't mean fast. It means, deterministic time. So many times that means fast, because, if a system is fast enough, like I said, then you can slow it down and meet, those. So for example, you have a camera that, looks at frames. If it needs to have, 50 frames per second, right? If it's very fast, it can do a frame, then wait, then do another frame, then wait, then do another frame, then wait. If it's slow, it will miss frames. But real time means, 50 frames per second. So it's not about being fast. So ChatGPT, you want to be fast enough so that you get the, the result in a time that, doesn't annoy the user, but it's not real time. That's not real time. That's, I mean, sure, colloquially you can call it real time, but from a, formal kind of engineering point of view, that's not real time. That's, high performance. That's fast. Yeah, so right, but this actually, so this is really real time because, again, it has to do with with the real time. Real time means, the way time flies, 60 seconds per minute and all that. Yeah. Yeah, so there are, typical applications, some mosquito thing. I'm not sure if any of you has any of you, I mean, this is very, very bizarre, I might say, as an experience. Has any of you gone, I'm not sure, I probably don't have it in India, but, in the US, there are quite a number at this point. So these Amazon stores, they no longer have a cashier, and they no longer have, you don't get a receipt or anything. You just go in the store. You don't need to have a basket, to buy. You go in the store with your bag, and you just grab some stuff, you put them in your bag, and you go out. And yeah, okay. Uh-huh.
That they are working, and so I feel like how these things going.
Yeah.
It is cashless. It is kind of not cashless. It is kind of.
Well, yeah. I mean, they need to know. You need to be an Amazon. Well, I think you need to. I don't know. No, you don't need to be an Amazon, but you need to have a credit card on file with Amazon. So yes, they will take your money. Yeah. 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 And, and actually, yeah, they can even do face recognition. And but it's a very weird sensation because, it looks almost like you are stealing. That's what people that, do shoplifting do usually, right? They go into a store and they get something, they hide it in their pocket, they do something. And there is nothing of that anymore. So, you just go, you get what you want, and you go out. So, yeah, it's a very interesting. Oh, yeah. So, yeah, because they basically, yeah, I mean, imagine how it is, right? So there are all these shelves full of stuff, and you go and grab, a can of, Coca-Cola. So it needs to know, it's Coca-Cola. It needs to, and yeah, but it's very spooky, I must say. I mean, I felt a little bit, weird getting into that store and just getting something and going out. It's an interesting experience. Yeah. So another, so I talked about embedded systems. Another kind of important, TLA, three-letter acronym that comes. More and more actually into the picture is this called IoT, Internet of Things. How many people have heard the term Internet of Things? Okay, so I'm not going to spend too much time, but yeah, it's this idea that now kind of everything will be somehow connected to the internet. And, that means that, you are going to have all these devices everywhere, kind of communicating with each other, sensing the environment, making, inferences about what's going on, sending alarms when something wrong happens, and yeah, so and all these growth in the everything is kind of exponential. And here again, Professor Ambika talked about security. So you have, once you have all these IoT devices and embedded systems in the field out there, they are exposed to all kinds of threats. So, that's a huge thing to deal with. Another, so here I'm kind of making connections between TinyML and, different aspects of things related to edge, aspects. So, another term that's another three-letter acronym, CPS, Cyber Physical Systems. This is actually a very relatively old term, but it's become more and more used nowadays. And it's this idea that you have a cyber part. So cyber is a very old term for computing in some sense. So I'm old enough, but in the 60s and 70s, there was a whole field that was called cybernetics. And really, cybernetics in some sense means computing. But actually, this term, cyber physical systems, was in many ways coined by someone at my university, by Jack Stankovic. So you have cyber, you have the computing, but then you have the physical. So physical means, things that you really can touch and, interact with. And, all these examples that we showed, the toaster oven, the self-driving car, the smart fridge, all the store, the Amazon store, all these things are cyber physical systems because basically they have, a lot of computing behind, but they are also, a robot is a very, a clear example of a cyber physical system where there is this physical aspect, that makes it interesting. And you probably know that nowadays, basically all, devices that we interact with are becoming more and more cyber physical systems. Basically, a modern electric vehicle is literally a computer with wheels, so the computer part actually gives more value. So if you look at the cost of the car and all that, the battery and the electronics and all that is much more expensive in some sense than everything else, the wheels and the steering wheel and the chairs, and they are in some sense auxiliary. So it's more of a computer on wheels than a car with a computer inside. But again, the important thing here is that it really needs to have this feedback loop that has to do with doing basically intelligent actions. So there are all these things going back and forth between the computing part, the cyber world, and the physical world. And a typical example is in a factory, for example, where let's say you have a piece of equipment, let's say a pump in a chemical factory. And now, in the old days, I should say, or even nowadays, the way you do maintenance on such a pump, it's what's called preventive maintenance. So what you are doing, and actually with our cars, everyone is driving, almost everyone is driving a car, I assume. You need to change the oil. So how do you change the oil? Well, every, I don't know, 5,000 miles or, 10,000 kilometers. I'm not sure what the rules are in India, but, at some point, after a number of miles, you go and change the oil. And you change the oil to prevent the motor from becoming defective. But that's very suboptimal. because it's done based on kind of statistical, data about how motors, if they have oil at different temperatures, at different modes, people can drive, more aggressively, less aggressively. There's more dust, there's less dust. The oil itself is different qualities, maybe higher quality, lower quality. So the car can stay for longer times and then, run, once in a while or, run every day. But we change the oil kind of at the same schedule. That's suboptimal. What you can do with what's called predictive maintenance. With predictive maintenance, you try to monitor. Again, you need sensors. You need some kind of smart sensors in the oil somehow in the engine, and you need to look for signs that you need to change the oil. And typically, that's going to lead to savings. So that's kind of, and of course for that, you need a very good AI algorithm that can take, the data that you collect from the, whatever the sensors you have and, kind of predict when is the optimum time to change the oil. And of course, for the cars, that's less important because, the savings kind of at the individual level are not going to be amazing. But for factories that have, a gazillion of pumps running continuously, and right now the way the maintenance happens in factories is a person actually goes, to all these pumps and, maybe listens with their ear, or they have some kind of manual monitor. And so, this really is going to have a big impact on the industrial world. Another place where TinyML is going to have a huge impact at some point, and I know some of you, the students, I spoke with a few students that are working on kind of biomedical applications. Again, this is a very, again, emerging area, but also very promising area. Because again, you can monitor the patient and you can, when I say you have an AI model. And again, you need a lot of sensors, both on the patient and maybe in the environment, in the room. But you can do, all kinds of things like, early screening and diagnosis, early diagnosis of, diseases. Telemedicine, this is a very important one. And I'm sure actually in India with, such a large country, but in the US is the same. It's a very large country. The hospitals are in the big cities, but then you have all these remote areas where people really don't have access to advanced kind of health sources. So telemedicine, and at our university actually, there is a professor that works on this telesurgery. So you can have a mobile kind of robotic arm that can perform surgery, but it's not it's not a self-contained robot. It's not an intelligent robot. It's a robot that's still manipulated by a surgeon, a real surgeon, but that can be 500 kilometers away in his office and basically do this telesurgery. And again, this can save lives, and it's much more efficient than effective because many times you cannot transport the patient fast enough, and for this. And, once this becomes widespread, well, something fell. Yeah, so these are kind of related to TinyML. You have these devices that are both cyber physical and embedded systems, but you basically, they have sensors and they can have some intelligence. So headbands, badges, clips, smartwatches. I wear both the smartwatch and the smart ring, and the smart ring has helped me cut on my alcohol consumption because the smart ring knows right away when I drink. So it's a very good feedback. And clothes, smart clothes, actually, these are also quite, so some more, so these are the kind of the consumer electronics, and there is a huge, market for these in the US at least. And, I assume there's going to be, all over the world, but yeah, you saw that Meta has come up with these smart glasses, the smart ring. I showed you one on my finger, belt, shirt. Frankly, the belt, the shirt and the pants, I'm not sure that they are, to me, that's kind of annoying that, it becomes really hard to clean and wash. So those are, and socks, those are kind of tough for me to see how they are going to become widespread. But anyhow, and tomorrow, I talked with Professor Ambika, so I'm going to have an open session on kind of collaboration possibilities, between, US institutions and Indian institutions. And at my university, we have a cyber physical system lab that is called the Link Lab, and people, and I'm part of that Link Lab, but there are many others. So there is a lot of effort on these smart devices, also on smart cities. So again, smart cities, it means basically you have, the city itself becomes kind of a network, an IoT network, and you have sensors, in buildings, in rooms, on cars that move. And you can get, some, better outcomes to, to how a big city functions. So now some of the, the characteristics, and we already kind of talked about them. So the latency and real-time performance, the security, we talked about that. Privacy is a big issue, actually, and I'm not sure how to feel about that privacy thing, because obviously, the more of these systems are deployed, the less privacy we have. I mean, even this, like I said, this ring that tells me that I'm drinking, I guess, it tells maybe, the company that makes the ring that I'm drinking. So I'm not sure that I want the company to know, but I guess it's the price we have to pay for convenience. The power efficiency cost, on-device learning. So on-device learning, I already, this is an important one. So I already mentioned this, but this is another big difference, I would say, between cloud AI and, this TinyML edge AI. For cloud AI, it would be nice to have, lifetime continuous learning. It would be nice if they could learn, but it's not really necessary as long as the companies behind the cloud, AI, they do a good job, updating their models regularly, and And all companies right now, because there is so much interest in AI, they are doing that. So you don't really see this lifelong learning aspect as a missing thing. On the other hand, if you are doing an edge AI, a TinyML that has, on-device learning capabilities, there is a danger that, it becomes obsolete relatively quickly. And of course, even, there are these ways to do the updates over, but fundamentally, what you would really like to do is to have, on-device learning. And, a simple example is, let's say, a self-driving car, driving in Calcutta versus driving in Delhi versus driving in New York City versus driving, in Jammu is very different. I mean, there are many similarities, but there are also differences. And it would be nice if the car could learn, so initially it's going to be more tentative, more, but again, it would be nice to learn on, locally and be able to do better. How many people have seen a spider chart before? Yeah. For other things. Yeah, no, I mean, yeah, just, okay. So because this, again, you may have noticed that, in my lectures, I try to, talk about the topic, but I also try to teach my students, and now you are my students, concepts that are important, beyond just that field. So a spider chart is a very nice way to represent trade-offs. Again, engineering is about trade-offs in a multi-dimensional way. So in this case, you have 6 kind of axes. And, it's hard. Usually we can show trade-offs, between energy and performance, for example, with an XY axis, and that's perfectly fine. And you see trade-offs there. But when you have, multiple, more than 3, then it becomes hard to do it with the conventional 3D representation. And the spider chart is very nice. And also with the spider chart, you can have very diverse kind of metrics and put some, method to the madness, so to speak. So in this case, this is a spider chart for TinyML that shows, the trade-offs for these 3 aspects, which is, on-device intelligence, edge intelligence, and cloud intelligence, in terms of, these metrics: reliability, scalability, latency, privacy, diversity, and cost. And again, you see that, for example, for cloud, so in this case, clearly, it's better if you are farther away from, from the center. So the cloud, is pretty close to the center on all of these, which basically means that, that's kind of an argument for TinyML, in terms of cost, in terms of, I'm not sure about reliability, why it's here, but, scalability, latency, and, diversity. In privacy is not that, maybe, the edge intelligence is, it's not, so the on-device intelligence is better for privacy. And then I'm not sure, really the distinction between edge intelligence and on-device intelligence. I guess on-device is extreme on-device. So really on-device is the, Okay.
So
Yes.
in that spider graph, like, why are you saying that the latency for the cloud intelligence will be smaller? Like, will be having a higher latency, right, in that particular case?
Well, no, yeah. So maybe so basically what it means, it doesn't mean that it's higher latency, because you see, you want scalability. So in some sense, it should have their 1 over latency. So my point is that for all these metrics, the farther away you are from the center, the better. So that's the meaning. And no, you're right. And saying the same with cost, actually. So cost, if you are here, means low cost, and here high cost. Yeah. No, but you're right. I mean, it's not. Yeah, but yeah. So basically, the spider charts. When you have a spider chart, you need to put the axis such that if you are doing this, that's the best. Okay. So yeah, that's kind of the rule for the spider charts. Yeah. So yeah, I mean, and again, they didn't pay attention in some sense because they kind of assume that. Yeah, but that's the meaning of latency. Basically, what's the best what does it mean when you say the best latency? It really means the smallest latency. So, but that's, in some sense, you can think of this being best, not small or large. Okay, so what's the best cost? What's the best diversity? What's the best privacy? And that's why I said that the nice thing about spider chart, you can have metrics that are really not measurable. Okay, because privacy. How do you measure privacy? So it's this best versus worst, or diversity. It's best versus worst. So yeah. So in the spider chart, that's different than an XY. That in some sense, I kind of try to make that case. But yeah, that's the thing. The spider chart can have these non-measurable metrics, which is a little bit of an oxymoron, I guess. Yeah, so this is kind of, and we talked about this, you basically have, the training and the analysis. And so what's different when you do TinyML, you basically need to have this extra step, which is compressing the model. Because, if you go with the conventional algorithms, the model is simply going to be too large to fit and to have, the energy efficiency. And of course, what that really means is that, you are going to give up. It's always about trade-offs. You are going to give up some of the accuracy of the model. So these are the conventional deep learning frameworks, and I don't think I had a slide like this. I should have. Maybe I had one already in the first lecture, but it's kind of important to see all of them. Although, frankly, by now, like I mentioned, PyTorch is really the big, the big one. TensorFlow is still kind of, important, but there are, a few others, like Caffe and Theano. This is more but again, the reason to put that there is that you basically go from a model that's there is an equivalent like this for PyTorch, but I think TensorFlow Lite is actually more popular in the TinyML. But the idea is that you do the first few steps are kind of the conventional TensorFlow, but then you go into the TensorFlow Lite, where there is this compression and optimization of the model, and then you deploy it. And typically, you still deploy it on some kind of microcontroller, and there could be more than that. So it's not necessarily a microcontroller. In terms of networking, again, this is about the IoT aspects of TinyML. Here also, you do want to have all of these connected to the internet, but you cannot use the conventional kind of HTTP protocol, just because, again, it requires too much, too many resources and too much power. So there are these kind of alternatives. And again, I'm not going to spend time on these, but it's important to understand that basically for TinyML IoTs, you are going to have to use a much more efficient networking protocol. In terms of security, I'm not going to spend time. Professor Ambika spends a lot of time, but the idea is that, again, you have a lot of threats because these TinyML devices are in the hands of a potential attacker. So if there's something in the cloud, the attacker needs to break through the security. Everything is network, so basically the only attack envelope is through the networking interface. But for TinyML, the security breaches can be just because of physical access to these devices. For TinyML, so this is kind of going against what we've discussed until now, because in the conventional AI, these deep neural networks have really taken over, and they are dominant. For TinyML, because these are very expensive, if you take a deep neural network and you compress it aggressively to make it fit and have the low power, the accuracy goes down. And what happens then is that for that lower accuracy, it may be that a more older style conventional machine learning algorithm can be as efficient, as accurate, but more efficient, because again, it doesn't use this massive kind of number of max and whatever we've been talking about. And again, these are some of, and for those of you that are working on TinyML, you should always look at these they are still machine learning, by the way. So these are still machine learning, that you still train them, but they don't use kind of this deep neural network. They are more mathematical, more signal processing, you can think. But there are support vector machines, decision trees. I mean, in our group, we use a lot of decision trees because they and some other things that are interesting. For example, because we are talking about decision tree. So we use a specific type of decision tree called random forest. One issue, and we talked a little bit about it, and you may have read about it, with AI deep neural networks, is that they give a decision, but you cannot explain it. There is this concept of explainable AI. And the fact that, kind of modern deep neural networks are not explainable. No one can explain why, and how an AI model took a decision. Most of the time it's the right decision, and it's wonderful. But if the decision is not right, you cannot really explain why. And sometimes even if the decision is right, there is nothing that you can look inside and say, oh, okay, that's why it said, that's why it made the right decision. The nice thing about some of these models is that they are very easily explainable. So for example, decision trees, when a decision is made, you can go back on the tree and see at each, junction, why a decision was made. And, they are very nice. And because of that, again, that's another reason why, for some applications, you really do want to go to some of these more, non-deep neural network. Yeah.
Talking about the compressing the neural network, so are you talking about if there are hundreds of layers, like we will remove some of the layers to make that model fit into the memory of the microcontroller? Are you retraining the model after the compression? So that these are the two.
Well, right. So compressing the model, there is not just one. You are describing one method to remove layers. Another, is to reduce the number of convolutions on a layer. Another is to sparsify. So, for example, there are many methods. Another is to do quantization. So instead of having 16-bit or 32-bit computation, you can have 4-bit or 2-bit computation. So all of those are compression. So so there is not just one. And actually, they are all used. Again, the TensorFlight kind of optimization for compression, it tries all of them and it does all of them. Again, it's about trade-offs. If you remove half of the layers, probably it's too much. So you remove just, a part of there. If you remove, all the, so it's about trade-offs. How much can you remove and still keep, and there is this concept of sensitivity. Have you guys heard of sensitivity? So basically, the way to do something like this is to, so let's say you have accuracy as your, goal, and then you do a sensitivity. Sensitivity means if I reduce the number of layers by 1 and retrain, let's say, that's another separate issue, but, it doesn't matter. I just reduce the number of layers and, how much does my accuracy change? And, if I had 10 layers and I reduced by 1, so if I reduce my number of layers by 10%, what's the reduction in accuracy? So let's say it's 3%. Okay. Then if I reduce the size of each layer by 10%, okay, what's going to be my reduction in accuracy? Let's say it's 4%. If I reduce the number of bits by 10%, what? And each of those, then you have these ratios, delta accuracy by delta some knob. So these are called design knobs. So I have some design knobs. I turn the knob and I get some change. And then you look and see which ones is the more sensitive, okay? And which one is the least sensitive. And then you basically want to change more the one that's least sensitive and less the one that's more sensitive. And you change, this one by 1%, this one by 3%, and by doing that, and again, assuming that they are well behaved, because sometimes, they combine, but that's how this happens. So it's basically a process of optimizing.
So does the TensorFlow also take into account the retraining of the neural network? Because there was a paper by Ann Lipman called Optimal Brain Damage in 1990s or 2000, which you don't train the neural network, and if you cut out the layers or reduce the size, the accuracy degrades.
Yeah. Well, so again, the answer is training itself is a knob. So how much can I do without retraining? How much do I get with retraining? Because there is a cost to do all of those. So yes, in general, you do retraining, but yeah. Okay. So this is, so now I'm going to go over, there are just a handful of kind of conventional TinyML algorithms. So, on one hand, You can try to do in TinyML all the applications for, cloud, but then there are some applications that are, kind of just TinyML in some sense. Because, so they are part of, benchmarks for TinyML. And, kind of prototypical TinyML algorithm is what's called anomaly detection. So, and anomaly, and if you have a smartwatch, for example, yesterday I almost fell, going up some stairs, and my watch, detected that I had some kind of, was that a fall? Are you okay? Should we call the, the ambulance? I was okay. But yeah, that's the thing. So, there is this very simple AI model that's monitoring, something, heart rate, breathing, yeah, maybe in this case with falls, it's the acceleration, right? For the example with the pumps in the, in the factory, maybe detects, the vibration of the pump, and if there is, a change in the vibration, and basically it raises an alarm. A typical example is intruder detection. So, you have a house and, it listens, if a glass gets broken, or if, maybe a sensor that detects, the door has been forced, and, it throws an, or, the typical actually that probably everyone has in their homes, a smoke alarm, in the ceiling that is, looking for smoke. And, as always, with these alarms, so, and some of them are pretty dumb, right? Like the smoke alarms nowadays, they don't have any intelligence, but, it would be nice to have intelligence. And for example, when you cook something and it gets burned, and, I would rather not have the smoke alarm, tell me that I burned something on the stove, because I know I burned something on the stove, and, I don't want to go and have to deal with it. So there is this, false positives and false negatives aspect. So, false negatives are clearly the more dangerous ones, because, false negatives basically means there is something that happens and, the model does not detect it. So that's really very bad. But false positives can be also very bad, because again, like with the smoke alarm, if it bothers you every day, then you take the battery off and you say, okay, I'm going to live without smoke alarm. And that's not good. But, these are some examples of using them for looking for tumors on X-rays. Some, again, example of, event detection. And again, I'm not going to, we are running a little bit late. Let me try to wrap up. Another, TinyML kind of algorithm, which is important, is, biometric face recognition. Another kind of TinyML algorithm is segmentation. So trying to understand, this is with a smart camera that's looking at a parking lot to try to understand where the cars are, where the people are, where the trees are. A very important one, this is something that's used in kind of the Hey Alexa, Hey Siri, all these kind of voice assistants that are available. Yes, a question online? Oh, okay. Or, well, if there was an Alexa here when I said, hey, Alexa, maybe that's what it is. so, actually my first PhD student, worked at a company called Sentient that, their claim to fame is, the lowest power chip that does this keyword spotting. Oh, yeah, I'm not sure why. Interesting. Yeah. Yeah, somehow something happened. But the good news is we are almost done. Or maybe that's what happened. So maybe this is the last. No, yeah, this is the last line. Yeah. So now, okay. So I think really Alexa heard me and is playing games. The important thing about this keyword spotting is that they need to be on all the time. So because again, you want to have these smart devices, maybe your phone or your smart watch or smart glasses, and you want these things to react when you are talking to them, but you don't want them to always listen to everything you say when you are talking to your friends. And if they were listening all the time, it would take a lot of power and energy to always look for the Hey Siri or Hey Alexa or things like that. So that's why all these devices that have this capability, they actually have two separate chips basically, or it could be on the same chip, but two different blocks. And the one that does voice recognition, full, where it can recognize everything about, that's turned off most of the time, unless you are talking to it. And the only one that's always on is this one that's looking for just Hey Siri. And this one needs to be on all the time. And when you have a battery thing, you really want to save the battery. So this one really needs to be very, very low power. So this is, a very typical example of a TinyML. And we'll talk about that in the second half of this after Professor Ambika takes over and talks about some reliability issues. Okay, thank you. I'm not sure. Do we take a break or no break? Okay, so 20 minutes break and we'll be back with some...
maybe probably 11 o'clock.
At 11 o'clock, we'll be back with some reliability part.